Okay, we've got Muirhead's theorem, and I'm going to observe that this sequence here, n, 0, 0, all the way through to 0, majorizes, it's very difficult to write that neatly, majorizes 1, 1, 1, all the way through to 1, n terms. Well, there's got to be n here as well. So what does that tell me about what inequality can I derive from that? Well, basically it says that 1 over n factorial sigma factorial, or sigma over summatations, of x 1 to the n times all the other terms to the power 0 is greater than or equal to 1 over n factorial again times over of x1, x2 up to xn. Okay, well, let's just have a think about this. That's the left hand side, which we know from Muirhead is greater than or equal to the right hand side. Let's just have a look at the left hand side. 1 over n factorial. This is why I like the 1 over n factorial notation. Sometimes you'll see Muirhead's theorem without the 1 over n factorial, but I like it because it reminds you that there must be n factorial terms. So let's just write it all out. Well, it's x1 to the power n, x2 to the 0, all the way through to xn to the power 0, plus lots of other terms, all of which start with x1. And of course there's going to be n minus 1 factorial terms there because we've got n minus 1 factorial here. Plus x2 to the power n times x1 to the 0, x3 to the 0 because we've got an x2 there, so the next one's x3, x4 to the 0, plus all the way along. And we've got another n minus 1 factorial terms because we can rearrange these guys in any way that we like. And so on. Plus x to the xn, to the power n, times x1 to the 0 all the way through to xn minus 1 to the 0, n minus 1 factorial terms. So the left hand side equals 1 over n factorial times n minus 1 factorial x1 to the n plus, from this row here, n minus 1 factorial times x2 to the n from that row there, plus all the way through to n minus 1 factorial xn to the n. Well, that's quite nice. That's just 1 over n times x1 to the n plus x2 to the n plus dot 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 plus xn to the power n, all in brackets. That's the left hand side. What about the right hand side? Let's have a look at that. That's 1 over, it's this one here, 1 over n factorial times that lot. So the right hand side equals 1 over n factorial times sigma factorial of, x1 to the 1, x2 to the 1, dot dot dot, xn to the 1 equals 1 over n factorial times, well, it doesn't matter how you arrange those x's, those x1s, x2, x3, they're all to the power up to xn, they're all to the same power. So we can shuffle these guys as we like. So there's going to be n factorial terms, and they're all going to be the same. It's just x1, x2 all the way through to xn, which equals x1, x2, up to xn. So overall, what does it tell us? We know that the left hand side is greater than or equal, let me write that out again, left hand side is greater than or equal to the right hand side. So it's 1 over n, x1 to the n, in brackets, plus xn to the power n, greater than or equal to x1, x2, xn. That familiar? It should be familiar, because if I write that yi equals xi to the power n, xi equals yi to the power 1 over n, that tells me that 1 over n times y1 plus dot 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 plus yn is greater than or equal to y1, y2, all the way through to yn to the power 1 over n, which is our old friend, the arithmetic geometric inequality, which you have derived from Muirhead's inequality, which is quite a powerful thing. In fact, I'd go so far as to say that the proof of the AM-GM inequality from Muirhead, I think, is the best proof of the AM-GM inequality. It's certainly the most general, it's certainly the nicest, certainly the cleanest. You don't need to muck about with this going up and then coming down. It's a nice, clean, clear proof. I think that's an absolutely beautiful little piece of reasoning, that. What I'm going to do is I'm going to stop here. I'm going to give you one more example and then I'm going to shut up about Muirhead's theorem because I'm fed up a bit. Done.